Next, we're going to talk about the unit tangent, the unit normal, and the binormal vectors for a vector function. So where is this coming from? Previously, we talked about the vector function r and its tangent vector dr dt, which we could also think of as a velocity vector. So now we're going to expand on that idea. Now this is coming connected with another idea. When we think of xyz coordinates, we can represent those as vectors, as the ijk vectors. Now those are useful for indicating directions in three-dimensional space. So what we're going to do now is, given a point on a parametric curve, we're going to determine three perpendicular directions, just like ijk, but ones that have special properties relative to the parametric curve. So first of all, we know that when we have, with the curve, we have a tangent vector, which would be dr dt or r prime. Now, what if we just wanted to turn that vector purely into direction? As we talked about previously with vectors, we turn it into a unit vector. So here we go. So the unit tangent vector, t, it's capital T, has the same direction as the tangent vector, but has length 1. So it's just defined as the standard derivative vector, r prime of t, divided by its magnitude. So that is sort of a unique way to describe a tangent direction, given a parametric curve. Next, we want to talk about a perpendicular direction. Well, here's the issue. There are an infinite number of vectors which are perpendicular to the curve. We're going to find a special one. Because the magnitude of the unit tangent vector is 1, meaning it's constant, we know that the vector dot its derivative equals 0, and therefore the unit tangent vector and its derivative are orthogonal. That was a fact that we previously showed. So therefore, the derivative of the unit tangent vector is orthogonal to the curve. And then subsequently, because we want pure direction, we're just going to make it a unit vector, so we're going to divide by its magnitude. Therefore, this is called the principal unit normal vector, or generally we just call it the unit normal, and that's big N, and that is the derivative of the unit tangent vector, big T, divided by its magnitude. So notice that we're imagining that we're in three-dimensional space. We have the tangent direction, we have a unit vector for the tangent direction, a unit vector for a perpendicular direction. And now finally, we need one more vector, which is perpendicular to both of those, to sort of manage our three-dimensional space. But we know that we can make a vector perpendicular to both t and n by taking the cross product. And this is called the binormal vector. So we call that b, and that's just t cross n. And then finally, we want to make it a unit vector because we only want it to represent direction. But notice that it's a cross product, so its magnitude is just the magnitude of t cross n, which is the magnitude of t times the magnitude of n times sine theta. But since the t and n are perpendicular, sine theta is just 1. So this cross product already has a magnitude of just 1. So we're all set. So this gives us a way to construct at any point on a parametric curve three unit vectors, one in a tangent direction and two that are in perpendicular directions, and all three vectors are perpendicular to each other. So it is almost as if every point on the parametric curve in space has its own xyz coordinates. And that's what T, N, and B do. So the calculations for actually calculating t, n, and b are actually, well, to find t is very easy. You just take the derivative of the position vector and then divide by the magnitude. That's relatively straightforward. Subsequent to that, the calculation to find n is rather tricky, or rather lengthy, I should say. And then after that, you take a cross product. So the calculation to find b is even lengthier. So we're going to do an example where we're just going to find t. So for this position vector, r equals cos t, sine t, 3t. It says find t, n, and b. We're just going to find t. So t equals the derivative of the position vector divided by its magnitude. So we get a unit normal. So we get a unit vector. And so dividing by, let's see. So first of all, the derivative is just going to be negative sine t, cos t, and 3. And then we need to divide by the magnitude. So we'll just say times 1 over negative sine t squared plus cos t squared plus 3 squared, and then square root of all that. And so there is your t, your unit tangent vector. And then subsequently, we could follow the formulas to find n and b. The calculation is quite long. So this is one interesting way that we can make vectors with a special relationship to the parametric curve at every single point. The unit normal, the unit tangent, and the unit normal, and the binomial.